Lost a fair amount of people again. So if I yell, it lasts only once.
Probably gonna go back.
How is it? How does it work? Oh, my wonderful. Uh, okay, I think we're ready to go. Again, for people on a live stream, maybe they don't watch the beginning of the live stream. That's why they missed the yelling. But again, our attendance dropped again, so this is not a case. So I will threaten you again with the in-person lectures only, unless you show up. So, but okay, so starting with that. So, are there any questions on anything like grades, homeworks, anything before we even start? All good for now. Our next homework is coming out soon, so hopefully today, and it will ask you to implement, as I was saying, a tiny memory allocator similar to x86, but on top of your homework, which we submitted already, right? And a function which maps a virtual address into a physical address, right? So it's kind of like memory map in x86, right? And walk page directory. But today our plan is following. So we remember last time we covered the case where the interrupt was processed without the change of privilege level, right? And today the case, which is a more generic case, is to consider what actually happens when the change of privilege level is required. And I will explain what the privilege level is, right? Because I never really carefully defined it, but we will do today. Okay, to start again, to start on what does it mean to change a privilege level? So if I ask you a question, so does anyone know what privilege level is?
Like priority or how much that's impact.
In a way. Wait, hold on. But can someone give me a more specific answer?
You don't want users to access.
At a high level, yes. So the intuition behind it is that you kind of want to split a system in two parts. One is user. Guys, just stop chatting because I cannot concentrate. One is kernel, right? And you want to make the kernel privileged and user unprivileged. And what does it mean to have the kernel privilege? What do you think it means?
The kernel has access to certain parts of the system.
Almost correct. So the first part of your question, first part of your answer, when you say there are some parts of hardware which are sensitive, meaning that if you let user access those parts, like for example a page table, you will immediately destroy all isolation guarantees because the user can change the page table, it can do anything with the address space with the entire system, right? You can similar for like a global descriptor table, right? However, when you started saying device drivers and file systems, in modern systems, it's actually possible, and it's not very hard to run device drivers in user level and make it's called a device driver, device bypass. So essentially the device is bypassed to the user level, and the hardware provides enough control so that the user can only access the single device and in a secure manner without breaking any security guarantees. Similar for file systems. So there is a trend to push as much stuff as possible outside of the kernel, right? But you're right that there are some parts of hardware which are sensitive, right? Okay, so that makes sense. Okay. And at a high level, our idea is that, okay, we have to answer the question. So how do we achieve those security guarantees? Like how do we ensure that the user code cannot access the kernel memory, right? And this is provided with this idea of a privilege level. And that's why essentially, I mean, there will be multiple guarantees, but this is one of them. Okay, so what is it? What is this privilege level? So it turns out that the entry in the global descriptor table, this is a descriptor, right? Has a field, which is a privilege level. This is the field. The field itself is only 2 bits, right? Because you only need to encode 4 privilege levels, 0, 1, 2, 3, right? 0 is the most privileged, right? So when we create a global descriptor table, we write this field, operating system, when it boots on later on, when it transitions between user and kernel, make sure that it chooses the entry in the GDT in such a manner that the privilege level is configured correctly, right? Again, like a little bit of confusion, right, on your faces. Let me remind you how it works. Remember, like again, segmentation. Partially, I mean, I told you that's why I'm teaching segmentation, because I want to explain the whole story. Remember, we have 2 parts. The offset sits in the register, segment selector sits in one of those registers like code segment, data segment, stack segment, right? So in your homework, if you suddenly did not clear those segment registers to zeros, for example, right? And you load a new global descriptor table, you were crushing, because GDT was actually, not GDT, sorry, Grub was actually configuring a different global descriptor table, right? Like, I don't know layout of that table, but it was different from what we did. Okay, cool. So segment selector chooses an entry in a GDT, and this is specifically the entry we were talking about, right? So everyone now on board with this, right? Okay, and then it, whatever, provides us with a linear address. It's less important, right? But the important part that we can configure this privilege level in the global descriptor table entry. There is also a notion of a currently running, that notion of a current privilege level, meaning that the system which runs the code runs at a specific privilege level, right? That's not surprising, because the entry in the GDT chooses the privilege level and says, okay, your current privilege level will be this if you're executing with a code segment from this, like with a CS register loaded from this entry in the GDT, right? Is that clear? So essentially okay, go ahead, question.
Are privileges only associated with executable regions? Or could you have like read-only regions with high privilege levels?
Well, hold on. So, correct. So, first of all, when I was talking about it, I was assuming that this entry will be loaded in the code segment register, right? To select the current privilege level. The current privilege level says, okay, you're running with a specific privilege level. The question is whether you can access specific regions of memory, right? And then when in a homework, we were creating only 2 entries, one for code, one for data, right? Code and data segment. In XV6, we will see today, it creates actually more entries, because it will say, look, when you're running at user level, you can only access the data segment with a specific privilege level. So you're right when you say that, okay, cool, you're running at a specific privilege level. Can you access the data? And yes, it's configured in a similar manner. Let me explain it in a second. So, okay, so what are the rules? So the rules of access. So the current privilege level can only access less privileged segments. So for example, 0 can access all of them, 0, 1, 2, and 3, right? That's natural. 0 is the most privileged. That's how they defined it. 1 can access 1, 2, and 3 can access only 3. So if we run user code at privilege level 3, user can only access data segments with privilege level 3. If you try to access something in a kernel, you will crash, right? Is it clear? Okay, cool. And of course, to answer, like to follow up on what you said, like the idea of this current privilege level, essentially CPU says that some instructions can only be invoked or executed at privilege level 0. And those are special sensitive instructions like load global descriptor table, LDTR register, right? LDTR instruction, move something in a special control register. We know like 4 of them, CR3 holds the root of the page table, right? So if you try to execute those at privilege level 3, then you immediately get an exception, protection violation exception. We will cover them today as well. That clear? It makes sense, right? Okay. So how do we configure those privilege levels, right? So again, back to boot. So when we started booting on x86 or similar to your homework, you say, okay, I will configure some GDT. When we do this long jump, right? So we choose an entry in GDT. So here for simplicity, I just, instead of saying like shifting by 3, I just say 1. So it chooses entry 1 in a global descriptor table. This entry corresponds to kernel code. So it chooses the privilege level, chooses the privilege level 0 here, right? Which means that I'm saying I want to start running in protected mode with privilege level 0 because I want to stay privileged. Otherwise, I cannot do much with the machine, right? Okay, so, and that's essentially the reason why segmentation is still around. Intel could not completely erase segmentation and switch to paging just because they needed the notion of privilege levels. They probably could change the hardware design completely, but they chose to have this global descriptor table around. And that's why I teach it specifically. Otherwise, it's a little like we don't do much, right? Remember, when we configure the global descriptor table, we always set it with the access privileges from address 0 to the max FFF address at the top of the 4 GB address space, correct? And on 64-bit machines, it's actually, you cannot even set any other limits. Like Intel said, okay, since no one is using them, we just simplify the architecture, reduce the number of bugs in the CPU implementation, and make sure that you can only have a flat 0 to max address segment, right? But the privilege levels still stay. Clear? Okay. Let's take a look at how we define the GDT, right? So it's like you did it in your homework, and so it's easy. So you have an assembly label GDT, you use some assembly macros, or this is how x86 does it. In a homework, I said, okay, forget about assembly, let's do it in C. It's a little bit easier, more natural, but a similar macro, right? And in this specific case, this macro doesn't even like allow you to say the privilege level. But when you run x86 from C, we'll take a look at it like in 10, 15 minutes, there will be a flag which says, okay, are you specifying kernel or privilege level 0 here or user privilege level 3, right? Question.
Does this motivate jumps being the in order to change your privilege level?
No, I don't really know why Intel said that you cannot load the CS register directly. I think maybe it's related to some internal optimization, and they say maybe it's just faster, but I don't know the history why they do that. So technically speaking, like you saw how we did it in the homework, which simply said we're going to jump to the next instruction, which and switch the code segment register, right? So it's roughly equivalent to moving CS into just simply doing a move into CS, right? So it's almost the same, right? We just moved one instruction down the stream, right? But and you can probably jump to the same instruction. No, then it's a loop, obviously, right? So you have to jump to the next one, right? But it's equivalent sequence. So I don't really know. There is no good reason to say that there is this limitation. Okay, so now we're running in CPL at CPL 0. Everything is fine. How do we exit? How do we change to user code? Who can guess? Or user privilege level?
Jump to the user level.
Yes, we can jump to the user code segment, and that will be fine. That's one way to change. But Intel also provides this a return from interrupt instruction, which we'll cover today. And it restores the state of the user registers. And specifically, when you execute the iRet instruction, so return from the interrupt, you can choose a different entry in the global descriptor table. In this specific example, I choose entry 4, which points to kernel code, which is defined in x86 with descriptor privilege level 3, right? And this is how you exit into user, right? This is what x86 will do then when it creates the very first process. It just says, okay, I'm ready. I will exit back in user level at this specific privilege level, right? Okay. And then we run into CPL3 for a while. Everything is fine. And today we'll kind of like come back to this and say, look, when interrupt comes, it will transition you back into kernel, right? Because naturally you want to process interrupts into kernel. They're privileged. They might switch the page table, stuff like that, right? And not surprisingly, there will be a mechanism here which allows you to switch back the interrupt table. Remember, like even without switching the privilege level, I was saying that the interrupt descriptor table, the entry will have not only the pointer to the handler, to the vector of the interrupt, but also a CS value, right? And this CS value will be able to choose kernel code again, meaning that we will start running at privilege level 0, right? No, hold on, but maybe I'm missing your question. So what is, you've heard that the UADs are special or? Okay, so the question is following, and it's probably better to answer this question a little bit later in this class, but I will give you an insight. So what you're saying is that each process has a process ID, right? Or maybe even user ID on Linux, because user ID specifies, let's put it this way. So naturally, you want to say one user cannot access the files of another user, right? In Linux and other Unix systems, each file has a user ID. And you say you by default can access your own files and maybe someone else give you access to their own files, right? But naturally, you want to say, look, only the files which you own can be accessible to you. And that's the notion of user ID to begin with. However, you want to have a special user, which is called root or super user, right? On Linux and other Unix systems. And that's a user ID 0. And it's a little bit of a broken access control model because suddenly you're omniprivileged. You can do anything with the system. That's why everyone wants to become root, any attacker, and then just do whatever you want. There were different systems in the past which were controlling those privileges at a finer granularity. You say, look, you're special. You can maybe reconfigure the system, but you cannot access all the files. And they eliminated this idea of a special user ID 0 and just instead like used, for example, idea of a capability, specific right to access a specific resource. So if you guys ever access something like AWS, there is no like a special user there. Like you really need a right to access something, right? And this is how you configure. That's evolution of this access control model, right? In x86, there is no user root, right? So all users can access any files. And that's why I'm saying later in the class, this idea becomes more natural because there is no access control in x86, but on Linux and other systems there is. But it's kind of broken in a philosophical sense. This access control is insufficient, and that's why Linux has all the like additional infrastructure to kind of reduce the power of the root and reduce, like you can do sudo, but a specific command, but not everything, right? So that's the idea. Question.
So are super users
No,
it's just a backdoor?
No, it's not a backdoor. It's a power to execute specific system calls with specific arguments. So for example, read in the super user root on Linux is still like a normal user process, but it runs with user ID 0. The kernel checks, for example, on access to every file. It says, okay, the access is allowed. You can access any file in the system, right? That's kind of how it works, but it's still a normal user process. And the kernel is still privileged, right?
So the kernel is allowing the super user.
Correct. There will be just a literate check if ID matches the file, access if 0. Okay, good. There was another question. Same. Okay, cool. Okay. Yeah, so user IDs are not related to privilege level. Privilege level just controls what I just said: privilege instructions and access to data. Okay. I said 4 privilege levels. In practice, all the systems which are run today, or almost all of them, Linux, Windows, stuff like that, use only 2 privilege levels. One for the kernel, which runs at 0, and one for the user, which runs at 3. And moreover, they used something what is called this flat segmentation model. All the segments in the system, no matter whatever you create, at 0 and at 3 cover the entire address space. And this is what we've seen, right? No, we haven't seen it yet, but we will see soon in how, when we say, okay, when we say x86 boots and it configures this global descriptor table to cover the entire address space, right? Right, so let's see how it does. So this is specific code in x86, right? So essentially, remember, we are back to main here. We did take a look at kinit, which initializes the page allocator, constructs the address space, and this function seginit essentially initializes segment descriptors. So what it does, it says, okay, by the way, I have an abstraction of a CPU. Why is that? Each CPU will have its own global descriptor table. I will ask you a question in a second why. You will have to answer, but just bear with me. This CPU data structure, the struct CPU-C, is defined as just like a C data structure like this, and inside it defines a GDT with some number of entries, right? This is very similar to how I taught you to do that in your homework, right? So essentially, it's done in C because no one wants to deal with assembly. There are some other fields which doesn't matter, right? Like again, we keep talking about it, but this is the entry in the GDT looks like that. We discussed privilege level. I mentioned many times that the base itself is split into like multiple chunks, but conceptually it's the address from with a 32-bit value. It's just like for historical and compatibility reasons, it's just split like this. This is the size of this segment, right? And we also seen that you sometimes configure read-only and writable segments, right? Limit actually is also split. And again, this is the C data structure, which, I mean, the reason I mention it, because we talked about it in the homework, but this is how C allows you to define a data structure with exactly the same layout. So for example, limit bits 0 to 15, it's a field of 16 bits specifically, right? It matches, let me erase everything on this slide. It's exactly segment limit 0 to 15. And it's the first field, right? The second field will be a base 0 to 15, right? So we see it here. And C allows you to say, look, I know that the hardware expects the data structure in this specific layout. And that's why C was designed this way to provide this layout, right? Okay, cool. And so specifically, we use a macro to like, most of these fields don't matter to us. That's why we omit them, but we say, and it looks nice because we say, when we configure something, we use this macro, which simply says executable and read-only. The start address of the base is 0, the max is FFF, privilege level is 0, right? So, and this is for the kernel code. For the kernel data, we specify, instead of executable read-only, we specify writable. Again, the entire address space, privilege level 0 again. For user code, we do the same and user data. However, now we say privilege level 3 to make sure that if you run at this level, you can access this segment, right? Because when you will be running at CPL3, every move instruction, you can only access the same or higher privilege level. It will check against this field in the global descriptor table, says, okay, it's 3, so access is allowed. So if you put something like 1 here, your user code will immediately crash, right? It's a good exercise for x86. Just try it and see how it does, how it goes. Any questions? Okay, cool. So relatively simple, right? So we say, look, use this segment descriptor, did it. And like now we see again that I convince you that x86 again uses this flat segment model, right? Everything covers all segments cover everything for both 0 and user level, cover entire address space. This kind of brings the question, right? So I keep saying that we use segmentation for protection, but I said that no matter, like, you really run the segments which cover the entire address space, right? So clearly they don't stop the user from accessing the kernel memory, right? Agree with this? Because it covers everything from 0 to max address. No matter which address you put in if you have a move instruction, loading something in the EAX register, here you put some adder. This adder can be anything from 0 to FF, all Fs, and the access is allowed because we just configured this global descriptor table. This entry, for example, which is user data, covers the entire address space here, right? Agree? So clearly allowed. Now I will ask you a question. So how do you think we actually protect the kernel memory from the user? I was mentioning it a couple of times, but I wasn't able to be concrete because we didn't have this knowledge of privilege levels and how they are encoded. Guessing. Correct. That's a good idea. We say, look, what if we don't map the kernel code? But what happens when we have to transition into the kernel, right? So you need to start executing interrupt in a kernel. So clearly, at least the beginning of the interrupt handler has to be mapped, right? Any other ideas? So Intel gave us this ingenious trick. They said, okay, there will be a flag in a page table, a specific bit, which says whether this page is accessible to the user or not. And that's what we do today. Like in a modern world, this bit, the combination of a privilege level, but a flat segmentation model. So essentially segments are not relevant. So they don't introduce protection. They just say, wow, they encode the privilege level and the bit in a page table. Okay, let me explain it, right? So this is how the world is configured on all operating systems today, or almost all, right? And x86 including, right? So the segmentation mechanism says you can access the entire address space from 0 to the max, right? To 4 GBs, right? That's your global descriptor table. Even for privilege level 0s and for privilege level 3, everything is from 0 to 4 GBs, right? However, you configure your page table and you kind of like, again, I use the same colors, like green and yellow for the kernel, green for the user, right? And it turns out that each entry in this page table at both levels actually has a bit. It's called a user bit. And this bit encodes the fact whether the page this translation through this page table entry is allowed at privilege level 3 or not, right? There is a couple of interesting details. It's a single bit, so it can only encode 2 levels, user and super user. So there are no 4 levels anymore. Intel said, well, no one uses 4 levels. We just reduce it to 2. It was a mistake. Historically, it was a mistake. They should have allowed more levels because today was the idea that, like we have to protect the execution inside the browser, inside a single process, maybe like some part of the process runs an SSH key. It would be nice to have special pages which can only be accessed when you enter a specific function, right? So you can access the key, but only through a specific interface, but you cannot really read it with a single move instruction, right? So, and literally the page table looks like this. So essentially for all the user pages, which are green here, we set the user bit here at the first level and set it at the second level. In practice, we can only set it at one level. So if you want to be a little bit faster, you can you can execute the security check right away here. And if the bit is not set, immediately trigger an exception, right? But x86 does it at both levels, right? No, sorry. For user, it has to be set, of course, at both levels. But for the kernel, you can actually unset it here, and then everything will be just fine immediately. Yeah. Almost. So let me complete my story here. So when you, for example, exit into user with an IRET instruction, IRET provides the code segment. Code segment chooses an entry for the kernel code in the global descriptor table. This changes your CPL from 0 to 3. After executing this IRET, for current privilege level, you're running with CPL 3. For example, you do a move instruction and you access kernel memory, like try to access the kernel memory. Since segmentation is always in front of paging, the hardware does the check against the user data segment, this kind of dark green one. But it allows the access because it says, I allow everything from 0 to 4 GBs, right? So this check passes, right, in hardware and silicon. However, after that, the hardware says, okay, but I have to resolve this page, for example, right? It goes through the page table, and if this bit is not set here, it immediately triggers a page fault or a protection violation, right? That's how it works. And this is how, like, all the system we run today on x86, ARM is a little different, but this is how they are configured.
So in the previous slide, only privilege level 0 to 2 can access, and the stack privilege level 3 can access. Yeah.
If set coded privilege 3 can exit.
Yeah.
Uh-huh.
But can kernel code, but when you were introducing the privilege level, you said that privilege level 0 can access data at lower privilege.
Correct.
So if it's set, could the kernel still access it?
Yes.
Okay.
Yeah. This bit is actually ignored at CPL3. I think this is how Intel defines it. Yeah, good question. Actually, this is a minor detail, and intuitively feel that, okay, it has to work this way, but I kind of forgot to mention, sorry. Yeah, so this bit is ignored like completely at CPL0. Okay, let me hold here for a sec. Any other questions?
Are there some kernel functions that are at the user level, so that like map, so that the user process can...
Okay, good question, but a little tricky to answer. Okay. Typically, remember, I keep saying, and it will become clear, not today, but next time when we cover system calls. If you think of a kernel as a library, which does some functionality, maybe print something on a screen, or like you say, mmaps, and mmap, or allocates a page like with this SBRK, right? So which intuitively means that user invokes a system call into the kernel, and SBRK has access to the page table, to the memory allocator, which we covered, like allocates a page from the memory allocator and maps it in a page table, right? And then exit back to the user, right? That's the normal operation of a syscall. And it's okay to say that all functionality of a kernel is exposed this way, right? However, obviously, as we move forward, like in the last 10 years, the hardware was becoming more and more efficient, like specifically high throughput IO devices, GPUs, network interfaces, 40 gigabits and higher, NVMe devices, which are like several gigabytes per second, right? People said, okay, this interface of a system call is too slow because with an interrupt transition, a system call maybe takes roughly 500 cycles. And if you do something like, imagine you're building a network router and you simply pass the packets from the input from like network cable, which comes on one interface, and sends them to the other. Maybe depending on the like VLAN ID virtual network, you choose which interface to send to, or like MAC address to send to, right? And you say, look, I spent literally less than 100 cycles per packet. So literally, I want to go with a speed of 100 cycles per packet. But the system call takes 500 cycles. So you have to find a solution. And so people started thinking of how to expose some functionality of a kernel to the user in such a manner that the system call can be avoided. And there are interfaces now which, like, it's a little hard to design because it's very easy to break isolation. Like, if you really have to touch the page table, there is literally no answer. But like, you can make sure that you can access the device driver from the user level. I mentioned it before. You can, for example, say some user libraries can be changed slightly by the kernel to say that on a specific hardware platform, you can benefit from a specific acceleration. So we will map a page which implements this functionality in user space, and you're not going to enter the kernel. So these tricks are done today, but normally not. But just be aware that you might see something like that in real life. Any other questions? Good.
One thing I'm still struggling to understand is, you said while explaining this a few times that if the bits don't match or something, that would be an exception. So if there is already something, like in my head, I saw that, like I used to think that this mismatch of bits is the exception. That's when it realizes that it can.
Right.
But if there's something underneath that is also able to detect incorrect behavior, then we have two more layers of
Right. Okay. So hold on. So first of all, like I don't know how, like you should think of a CPU at a high level CPU. You can write the CPU in C. There are special languages to program CPUs like Verilog and stuff like that, but they are roughly speaking equivalent to C most parts. And there are languages which can translate from Java to Verilog, of course, like with some tricks, like not all Java, but a subset of it, right? So you can think of a CPU which as of a thing which implements a specific logic of checks, right? And okay, let me show you how. So for example, let me end the slideshow for a sec here and switch to the web browser, just so we can quickly, what is this? Like, for example, this, we say, I want to see what IRET instruction is really doing, x86. So I go to, like, for example, there are multiple resources like that on the web, but it all comes from the, this web page comes from the Intel manual. I mean, there might be some details of this instruction which are not publicly known. People are, security researchers try to understand what's going on, but really this is the pseudocode of this instruction. It says, okay, if paging is 0, then go to real address mode, right? We didn't enable paging altogether, so it will switch to the special processing path and so on. And you can read it, and it's actually readable pseudocode. So for simple instructions, you will understand that, okay, it really does what I was expecting it to do. And so, and most likely it's not even implemented as gates. It's some kind of subprogram which runs on a CPU, right? Yeah, on Intel at least, right? And now you're asking a question. So first of all, like it's complicated logic, but I got it. I understand how it works, and CPU does exactly this. Now, why two levels of protection, right? So mostly the reasons are historical for backward compatibility. The first Intel CPUs didn't have paging. So paging arrived, first rudimentary paging arrived on X286 machines, was fully implemented on 386 machines. It's roughly, I would say it's late 90s. And we're still, like segmentation was, of course, from early Intel machines, and we're still dealing with it. So it's probably not good. Intel had a proposal last year to reduce segmentation, like remove it completely, stuff like that. There are some issues, and that's one. There are some objective issues. Second, unfortunately, Intel cannot always guess how to do it properly, because they are like, okay, tomorrow you're going to go work for Intel. You were not in this wonderful class, you know. You might have misunderstood how things should work, right? So it's hard. It's hard to give up old interfaces. When you design CPUs from scratch, like RISC-V, you can make it simpler a lot.
So so the microcode itself is not, is it sufficient to detect these?
Right. So like this is the logic. So you will see if you scroll here, like this is a triggering of a general protection fault.
Okay.
So this logic says, and why is it so useful to read this? Like in practical terms, why would I teach you to read these instructions? Sometimes you say, look, I was working on my homework, I'm crashing, I have a triple fault. How did I get to this? So this might help, because it says, look, I actually can understand why potentially this exception was triggered from this. I mean, it's very unlikely that you will really need to do that in this class, but in real life, when you graduate, that's most likely will be the case. Sometimes what we do in my team, we read the source code of QEMU and we trace QEMU, meaning that we trust QEMU to implement CPU faithfully. There are bugs in QEMU. So like if you take multiple versions of these emulators, they will all behave slightly differently, because people wrote it by wrote QEMU by essentially reading those pseudocode descriptions, right? And people make bugs. But in most cases, QEMU is correct, and we trace our execution of our kernel emulated on QEMU and see, oh, we forgot to set that bit, and that's why QEMU crashes, right? So we just print out a version of QEMU.
So this is where error is corrected.
Yeah. So essentially, this logic is implemented by the CPU, either as some of it will be implemented in silicon, real gates to make it very, very fast. And some will be implemented as pseudocode, which runs on the CPU and invoked when you invoke the IRED, for example. Good, so we understood. So all questions, anything else? Good. Okay, so okay, back to the lecture. So that's nice. So we finally, I mean, this is a major milestone if you didn't pay attention. The thing is that you finally kind of understood the complete protection model on Intel x86 CPUs, which is kind of cool because it's a little like involved, right? So there's segmentation, there are segments, entries in a global descriptor table, privilege levels, and bits in a page table. And again, if I only teach the page table, I can say there is a bit, but maybe my story is incomplete, right? But okay, we have a complete story. So we're done with this detour. We now understand what the privilege levels are. We're ready to start processing interrupts across privilege levels, right? Okay, so what needs to happen? So again, assuming we're running at user level, there is some kind of infinite loop which crunches the numbers, and suddenly, again, a timer interrupt arrives, right? So, okay, so this diagram is a complete or almost complete interrupt processing task. So at a high level, again, the story is like that. You were, enable my pen here. So you were running code here, your infinite loop. You were some stack here. This is your EBP register. This is ESP points here. Stack grows down. At some point, interrupt occurs. Hardware, very similar to how we were doing it without the change of the privilege level. The hardware says, okay, the interrupt arrives with a specific number. So in this example, it's a timer. So it's an interrupt number 32. We get the entry from the interrupt descriptor table. Remember that there is a register here, which holds the virtual address of the interrupt descriptor table. And this entry contains two things, right? So one thing is the pointer to the really virtual address of the interrupt handler. That's how I was explaining it last time. And the second field, which was not important last time, but important today, it's a code segment. It chooses the entry in the GDT. So meaning if you were running with CPL3 here, user level, you're choosing an entry, you can try to choose CPL3 again, and that's fine. You can structure a system like that. Maybe some interrupts can be processed at the user level. Again, for simplicity, x86 processes everything in kernel. So it chooses an entry for the kernel code here, and this entry will have this descriptor privilege level set to 0. Agree? And this is how we transition from 3 to 0, right? After that, our privilege level becomes 0, right? Agree? There is a couple of details. Okay, question.
So the interrupt itself changes?
No. Look the dependency here. So it's again, it's nice, but it's nice to have this detail. So everything starts with the number 32. 32 chooses an entry in the IDT, right? This has two fields which are important. It has more fields, but other fields are less important for us. One field is a code segment, which chooses an entry in the GDT. So if this code segment says like 3, it will choose entry number 3 here, right? In our example, I think it's 1, right? Agree? And suddenly this entry in the GDT here, which is kernel code, will have a CPL 0. And this is now, the next instruction will be executed with CPL 0, right? So we switch back into kernel. Details. We discussed it before. Can we continue on the same stack? No, why? It's not risky. You just open a door for a potential vulnerability. You can run, okay, if it's risky if you say you can run out of a stack space. It was like that for like 30 years. But then people said, okay, I can make money by exploiting systems worldwide, globally, a lot of money. And it becomes just impractical. So the user can, for example, set ESP to point somewhere here. User knows that something is very important in the kernel at this address, right? So, and depending on how the hardware behaves, it says, okay, I will just simply override this because it needs to save the registers, right? Right? And so that's not okay because it clearly overrides kernel memory. You can say something like maybe ESP is just set to a page which is not mapped. Like, I don't know, I will put it here, but it's maybe not a good example, but unmapped page. And then it immediately, hardware cannot save on the stack. You go into a double fold. And since the stack is still there, you cannot save on a stack again. You go into a triple fold. And this is what you've seen in your homeworks. QEMU just halts, but the real hardware reboots at this point, right? We got the point, right? We need the stack. Just to warm up a little bit, let's do a poll. Lovely, right? Actually, maybe let's do a poll a little later. Let's finish this. Sorry, like let's. I see that everyone is paying attention, so we can move forward without a poll. Okay, so we need a stack. So we agreed on that, right? Okay, we need a special kernel stack here, which is always well configured by the kernel, and the space is present, right? Of course, the hardware has to somehow figure out where the stack is, right? So what are your ideas? If you were designing the Intel CPU, where would you put this stack?
Already.
Well, maybe it was allocated. Maybe it was loaded at ESP, in the ESP register at some point. That's actually a very good question, right? Because it kind of clarifies what is happening. Remember, we were running in main, right, at some point. And to execute C code, we need stack. So clearly, there was some kernel stack at some point, and ESP register was pointing to it, right? But however, when we exited into user level, we switched the stacks, right? So user, when we started running user, probably ESP was pointing to the top of user stack, right? I will make it ESP user, right? So this kernel stack is there. There is memory for this stack. But here you're running with on the interrupt path. ESP points to ESP user, so probably somewhere over here. You do this transition, but you have to figure out this kernel stack. So you have to remember where it is somehow. So where will you put this data? The location of the stack. There are multiple design choices. There is not like a single good answer.
I put on the register since it's being
Totally. Which register? And you say like I will have a kernel stack, kernel ESP register, or maybe it will be like, yeah. So that's I think it's an okay design choice, and I'm sure that CPUs are doing that. There is nothing wrong with that, right? You say, I think there is an architecture. I think it's either parts of AMD like have this AMD like first of all. I keep saying there are only 4 privilege levels. It's not true. In real life today, there will be more. There's like some privilege levels for hypervisors and for some execution modes, which are even hidden from the hypervisor. I mentioned one. Remember I mentioned the system management mode, which is a special mode. And I don't even discuss it in this class, but yeah, it will have its own stack, right? So yeah, question.
Just a question. The privilege groups that I've seen in context of implementation and stuff, they're part of the same hierarchy. Like I've seen them being like privilege level -1, -2.
Right. So -1, -2, what we're like hypothetical. It's like it's not real hardware privilege levels. It's just to understand, to give you an idea that it's under. But yeah. They will be implemented differently through a different set of protection mechanisms.
Right.
So like really there will be different set of registers. And I don't want to talk about them because it will take us forever. Okay, but cool. So putting it in a register is a good idea, right? So why not? I'm saying that it's actually done. Intel chose a different path. Again, who knows why? Maybe historical reasons, stuff like that. They said, okay, there will be a different table. The table is called TSS, stands for task state segment. In the past, TSS was doing a ton of different tricks, but today it's really literally is used only for this, or maybe for one other thing. But specifically, there will be a pointer in a TSS which points to the kernel stack, right? So that's my pointer here. And there will be a hardware register. It will not be really a register, because you would imagine like maybe there will be a register which will be pointing to the TSS directly. No, Intel said, okay, by the way, you need an entry in the global descriptor table which holds the pointer to the TSS. So really like the connection is like this. There is a pointer here, and there is a TSS segment register which chooses this entry from the TSS. A little unusual, but works. Who cares? Like, as long as it works, it's just fine, right? But again, just don't get surprised that why am I teaching at this level of details? My goal is to make sure that you read the source code of x86, or if happens, you work on Linux or any other real operating systems, you read the source code, you see the TSS, you immediately know what's going on, right? Question?
So you have this introduced point.
Which points to the kernel stack.
Right, why not just keep that pointer in the
Good question. And again, so I think Intel's choice was driven by generality. There were like multiple cases because TSS in practice has multiple pointers. It can hold stacks for each privilege level. Privilege level 0, 1, 2, and 3. It just today no one uses anything but 0. But in the past they said, okay, cool. We will leave this world and embrace this idea that TSS will be like the layer of interaction, which will allow you to construct all these complex scenarios, but no one really builds them this way.
So like within an what
I will cover it in a second. I'll answer. I have a slide on that. And yeah.
Does the hardware follow these pointers to the stack?
Correct. It's all in the CPU. And if I switch back to the web page, which I was showing IRAD because there is no, like, if I show the int instruction, you will see that it like really like follows this path. And you can read it. It's just that there are so many if cases that you can easily get lost, but it's there. Good. So what's in the TSS, right? So TSS contains a ton of very weird stuff. And but I don't want to go into it. Why? Like, it's probably not practical in this class because in some corner cases it's important. For us, it's not. So that's why I'm saying it only for the purposes of our class, it holds only these two fields, the stack segment and the stack pointer for privilege level 0. And when we say we enter from user into the kernel, we completely have no idea where the kernel stack is. We'll pick it up from TSS. And also pick the stack segment because on Intel, everything needs a stack segment and maybe user role. It's also a security vulnerability. Maybe user, like somehow before entering the kernel, set their stack segment to point to something weird, right? Something non-existent, which will trigger like a protection fault because it doesn't exist in the global descriptor table. So the kernel has to protect itself, right? So a lot of these design choices are very carefully, despite the fact that I'm saying, okay, Intel failed multiple times, many of those design choices are driven by the security requirements to make sure that you can only enter into the kernel through a very controlled interface. If you want to use an analogy, it's a TSA at the airport. They will scan your luggage. It's very similar here. The kernel will check the input arguments to the system calls, right? But the only entry is through this gate, right? Okay, good. Okay, so, and here's the full path of, like, we have this slide for processing the interrupt at the same privilege level, but now let's take a look at what happens when we change the privilege level, right? So the hardware saves these two registers because they obviously, now they change, right? So we said, okay, when you're running at the same privilege level, you don't have to change the stack. But here, since ESP and stack segment are changing, we have to save the old ones, right? So we first save them in a CPU internal register because we don't really know where the kernel stack is, right? Then we will essentially load the kernel stack and a new stack segment from the TSS. And now we can start saving stuff on this new stack, right? So we will push these 5 registers. Who can tell me why we're pushing this 5? What is so special about these 5?
It's all the things you need for a context switch as well. So I'm guessing to restore state entirely.
Correct. This is the state which is immediately changed on this transition. The hardware chooses new values, and you need to remember the old values. That's why you save them on a stack, right? On this kernel stack. Everything else, you can save by hand. EAX register, you can just simply push it on a kernel stack because it's not overwritten by hardware. A slight detour, there is a different mechanism today to enter the kernel. I mentioned it, it's called sysenter. Why? It's much faster than interrupts. Like again, remember my 500 cycles, like bad for packet processing. So sysenter can be executed full pass, like 0 system call, enter and exit in roughly 115 cycles. So 5 times faster. So this mechanism actually overrides some general registers, like I think ECX and EAX. So it saves them. No, it doesn't save them actually. The ABI should be different and you should not hold anything in those registers because the interrupt, you will not be asynchronously preempted, right? With some a loop value in the EAX, you invoke a sysenter synchronously to do like a file read, right? At this point, you have to save the EAX before invoking sysenter. Question?
So it's like
Different, but that's what I'm saying. Like calling conventions are important and you have to know them, but it's slightly different calling convention, yet another one. But okay, cool. So we save these 5 because they simply disappear from us, right? Because we have to restore them. And at this point, we say, cool, we need to set the code segment, choose it from the entry in the interrupt descriptor table, choose the instruction pointer from the interrupt descriptor table to start executing the interrupt handler. And again, I keep talking about it. If there is a flag in the IDT, we'll cover it, like I will mention it later today. It can disable subsequent interrupts immediately. And this changes the eFlags register, right? So that's why we clear this bit in some cases, right? Okay, cool, good. Question?
If you're handling.
Good question. And so, I mean, I have a slide later, but think of it this way. In most cases, you do want to disable interrupts. But what about system call? System call is kind of like a regular call, but it has to change the privilege level. So why would you disable interrupts on a system call, right? It seems that like, well, if I want to do a printf on a console through a device driver, I don't really have to disable interrupts, right? And this is specifically the case where x86 configures the system call entry in the interrupt descriptor table to make sure that the interrupts are not disabled. But in any other cases, they are disabled, right? And we'll see how, like in a second, how x86 configures the IDT. Any questions? Good. Okay, now definitely time for the poll. Begin execution of the handler. Let's wake up. And for people online on the live stream, let's do a poll. Let me see what am I asking here. This one? Okay, do you see it? Do you you have the link, right? So go for it. Maybe switch from my slide deck so we will see the answers. You can only select one option. Man, really? Let me quickly edit. Can I edit? This is how it looks for me. So I say And it was the same bug was there last time, just didn't help, right? So when I was asking about where the kernel was mapped, right? But why is that not multi? It looks like this seemed to be correct, right? This is the way how I should run it, right? Respond setting, website, text messaging. No, yeah, this we can say, you can change answers, okay. Each option can be maybe selected, I don't know, 10 times. Let's do this. Now, can you? Okay, cool. Sorry, yeah. Well, we have a lot of faculty who work on human computing interaction, HCI. You can always laugh and say, like, what is HCI? HCI is about buttons, but this is example of a button. How, like, look, from the interface I showed you, right? It's clearly, it almost implied that you can choose multiple options by default, but you can't, right? And so, okay, so people who do HCI in this class, kudos to them. They work on good things. How can I present here? Present. Okay. So how are we converging? We still have people who believe that EAX is saved, maybe because they just clicked it accidentally. Some people believe that EBP is saved. So why is that? Anyone in the class, or everyone is only online people? Question. Right. But remember, and again, it's a very good question again. So remember that I said that EBP is only somewhat special. When you configure those compiler flags to say, maintain the frame, the stack frame, right? It will generate the code with EBP, but it has nothing to do with interrupt handling. And the ABI, just the calling convention is different for interrupts, right? And it's not saved at all. And in practice, I was saying multiple times that we really don't need EBP. But the question which I'm asking a specific thing, like what registers hardware changes, right? So that looks correct to me. Some people still believe EBP, so 1%. Okay, good. So clear, any questions on that? Right? Good. So let me close this. What do I do now? I wanted to actually ask you a different question. So which probably, depending on whether it requires a multiple, let's just like recap what is that how do we activate? So how many privilege levels are there on x86? Dummy question, but still, let's see. For everyone in the class, but for people who are on a live stream, just freeloaders on the live stream. 16 is a good option. I like 16. We should vote and send it to Intel. We need more privilege levels. Like hardware hasn't changed. So there are just additional security mechanisms which allow you to introduce additional, let's say, protection enclaves within a program. It gets tricky. So join me for like next fall for the advanced operating systems and I will talk about it. Okay, so everyone knows it's 4. That's good. Everyone answer it in a class, right? Good. So let's close this poll, exit. Last final question, which is important. Again, very, very goofy, simple, but important because we need to understand this. We say, which privilege level is most privileged? Yeah, I said it multiple times today, so we know it's 0 because, you can design it differently. But, well, yeah, some people are confused about it. Okay, 0, right? Agree? It would be nice if there might be an option to say how many responses we actually got. Now it's, there's a delay in the live stream, so everything agrees on 0 now. Okay, cool. So back to business. Back to our slide deck. Let me just deactivate this one. Oh, everything is deactivated. So back to the slide deck. Okay, so everyone is ready to go. Wake up, woken up. Okay, so and this is like I was saying before that this is the complete interrupt path. So the previous one was almost complete, and this one is complete, right? So instead of saving something on this stack, the hardware saves on this kernel stack, which is special here, right? Which is selected from the TSS, right? So if anyone ever asks you, explain me what happens on the interrupt, you quickly look up this slide and you can tell the whole story. If you listen to me carefully, it's very easy. And conceptually, it's somewhat easy. The gesture of it is easy. It's just that there are so many details. If you start reading from the Intel manual, you will get confused. But really, this slide is the answer to everything, right? Maybe a slightly minor patching should be done here to make sure that this pointer is clear, that TSS is, and there is a TSS register here. So that might help us a little, but otherwise we are clear.
So there's a cyclical reference between the TSS.
There is a what?
Cyclical reference.
A cyclic reference between the TSS and the GDT. Well, in a way, but it chooses semantically different things. So it's okay, let me explain. I mean, yeah, it's a good one as well. So there is a segment register which selects the entry in the GDT, which corresponds to TSS, right? So this is the register. It chooses this entry. This is actually, you see, I put size off here. So TSS is actually smaller than the entire address space. That's not surprising. This is one entry which Intel allows you to choose the size, one of them. Like there is a couple more, but not many. So it really says, okay, TSS is of this specific size. So this one chooses but other than that, it's base address of the TSS. It chooses the TSS. And then in the TSS, there will be a stack segment selector, because if you don't use the flat address space, maybe this segment is smaller. The kernel stack segment is maybe half of an address space, or maybe like the upper half, or maybe even smaller. Not done in practice, but still it's there, right? So that's why it goes here and chooses the kernel data segment, which has descriptor privilege level of 0, and the entire thing covers the entire address space in our case, but it can be different, right? That's the cycle here, right? Is that what you're talking about? But they're semantically different because you're not going to be running the cycle. The CPU knows what they're doing.
Is the TSS entirely protected, or can user level code access some?
Good question. Okay, it's actually a very good question indeed. So the question is following: is the TSS protected? Or I would change this question and ask differently. Any of these things, can user access any of these data structures? The answer is probably no, right? You might come up with a very, very exotic case where you can let user to do something, but typical answer is no. That's why all of them are allocated in kernel memory, which is of course protected kind of like recursively by the paging plus segmentation mechanism, and user cannot overwrite any of those. But they can invoke system calls which affect those data structures. And this is how the bug in operating system sometimes allows a vulnerability, meaning that if there is a bug in the SBRK or in a memory allocator, you might accidentally allocate the page which is already mapped for the page table to the user just because, well, you screwed up. The pointers are like wrongly added to the same list twice or something, and then the user suddenly can overwrite the page table. That's the bug, right? And we have roughly on Linux with modern vulnerability discovery tools, we are averaging at something like 150 to 300 vulnerabilities a year. And I'm saying that it's literally a tip of an iceberg because not every bug gets assigned a CVE. There might be 10 times more bugs. My favorite anecdote, right, which I keep bringing up, that I had a student who was bounty hunter. So he buys I told you that in the beginning of the class, he buys the newest Google phone. Software is open source, right? And he starts hunting for bugs, and then he finds vulnerability in the Android software stack and submit them to Google. He made roughly 150, from 80 to 150K while maybe 80 while being still a student, and maybe like more in his next year while he was still doing it, working for Intel, right? So it's a jolt, right? But he was also complaining that he was always outgunned by big Asian teams, which have like literally have government support to back them up. And he's his friend working against teams of dozens of people, right? But this is the end of the story, right? So you can do this. It's useful knowledge. Okay, good. Answered the question. Okay, so fine. So just again to compare, this is our stack. So the user stack, nothing gets saved here. Everything gets saved here on this on the kernel stack. This is different from what we've seen before, where if we don't change, no change of a privilege level, everything gets saved on this user stack, right? So, but other than that, the routine seems to be similar, right? Again, that's the complete figure. Now, okay, we understand how it works. Let's let's be more specific about what is there in the interrupt descriptor table. What kind of interrupts we can configure, what can be running. So on Intel, the interrupt descriptor table looks like this. So the first 32 entries are reserved. This slide is from a couple of years ago. So Intel slowly keeps adding new special interrupts or special exceptions, because they add extensions to instruction set. So here we have SIMD instructions, but maybe they added some AVX instructions, and maybe they could cause additional exceptions, but they still optimistically believe that they can fit all exceptions in this 32, right? So those are fixed. This is like the contract between the software and the hardware, right? So for example, when you have a bug in a page table, you will get a page fault. So exception number 14, right? And let's go through all of them. So this is when you divide by 0, right? So division by 0 causes an exception delivered through the vector 0. Debug exception. So essentially, there is a way on Intel to install something what is called a watch point, or like a hardware breakpoint, which says, okay, if this instruction gets executed, you immediately get an interrupt, right? Or get this exception, right? There is another debug exception, which is called a breakpoint, which is used by GDB when we insert a breakpoint into software breakpoint. So essentially, there is a specific instruction which has an opcode XCC, which if you have some like a move instruction which moves something, and imagine it occupies, let's say for the sake of the argument, 5 bytes in memory, and you say, I want to break point, I want to break into the GDT when I execute this move instruction, this move gets saved and XCC gets written in memory instead of the first opcode of the move instruction, and then when the CPU reaches it, it just immediately exits, and goes it goes to the operating system, and then operating system passes control to the GDB. That's how GDB works. I'll give you a concrete example. Imagine you wanna, and it doesn't happen too often in practice, but can happen. Imagine you wanna see not when the move instruction executes, but when it touches a specific address in memory. Maybe it's some data structure, maybe it's GDT. And you say, well, something in my program overrides GDT. I don't know what, but I wanna see what. And you say, look, I want to see when this address gets written. And this is the case for this debug exception. You can install, hardware has support to say, I will be monitoring the memory bus. The moment I see this address, I will trigger an exception. And that's kind of useful because you cannot do it you can do this trick. You can say, well, what if I map this page, the entire page, which contains this data structure, as read-only in a page table? That's a way to do that, right? So you can monitor accesses to this memory location. That's one way to do it in software, but sometimes you want, and then you trigger an exception, you see which address, if it matches, then you trigger debugger. If not, then you move on by remapping this page as read-write, right? But hardware has a little bit of support to prove it. Reserved means you cannot use them in software. Intel says, I will use them in the future. And what I was saying, this table is probably from 3-4 years ago. And if you open the Intel software developer manual, it comes from the Intel document, right? Called software developer manual. There will be new entries. related to virtualization and new other extensions. No, like all of these 32 are reserved. The first, I'm going in the order, right? The first already defined by Intel. These ones from 20 to 31 were reserved for the future use 5 years ago. Maybe 20 and 23 are already defined, and they hope they will fit in 32, right? You got it? So if you open it up, you will see new entries, which I don't have on the slide. Question.
So entry number 7. Nice. So this is like, I'm guessing this interrupt happens if it's trying to use macro processor.
Right.
How does like couldn't there technically be thousands of interrupts that this device doesn't exist?
Correct.
Like you can have a RDMA doesn't.
Right. So some of these are historic. So, and specifically this one, because on modern CPUs, the coprocessor always exists. It's just that early in the days, the mass coprocessor was kind of like a GPU today. It was a separate chip. Like there was an Intel CPU, which could only compute integer numbers. And there was a different piece of silicon available on some machines, which were doing the floating point. And probably, and I'm not exactly sure how, but I guess it's historical, so I don't know the details. I never touched it myself. Probably the deal was that if your mass coprocessor doesn't exist, you see a floating point instruction, it allows you to emulate the floating point instruction in software.
Oh.
And maybe like provide some compatibility. But those mass coprocessors were like predecessors of modern GPUs. They were completely different, nothing parallel, but it was same idea. You want more compute, floating point compute, you need a coprocessor. Today, Intel machine has, of course, all the floating point engines and has vectorized instructions and stuff like that, and some crypto support as well.
Just one last class I asked you about like different devices enabling their own interrupts. Does that happen in the master build?
Right. So let me just get to it like slowly. Yeah. So yeah, the device interrupts are here, right? So my next slide is about it. So sorry, probably. Okay, so we have a couple of there is a special non-maskable interrupt. I will explain it in a second. Breakpoint, I explained. Overflow, again, back in the days, it was a big deal, like integer overflows because you do plus plus and it just goes out of range. So you will get this interrupt. Out of bounds, forgot exactly what this one does. Again, no one uses it. Undefined opcode used by programming languages like Rust, for example, to implement panic. So when you say, look, you really shouldn't know. I mean, like, what was it historically? I don't really remember. But today, you will see this exception when you really hit a part of the program which never should be executed, right? So you will see this undefined opcode. Mass coprocessor, like roughly discussed already. Double fold. We talked about it, right? We've seen them. So you try to execute an interrupt pass or exception pass, and suddenly something goes wrong. It triggers a double fold. So maybe you're luckier, and maybe like, for example, you forgot to install the entry interrupt distributor table for the divide error, right? So just there is null, or CS points to something, or the base of the handler points to something, some rogue memory. So then you handle the double fold. Don't remember the 9, invalid TSS, obviously, right? So TSS is not well formed, so it may be present, but maybe some fields are not aligned properly or something. Like similar for segment not present, stack segment not present. So like again, may happen in your homework when you forgot to configure SS properly. General protection, this is a good one. So remember in my previous, I read pseudocode where they were calling GP, right? GP was an error code of 0. So this is one specific, remember I said that some interrupts or some exceptions specify an error code. And so we were specifying it was GP0, right? So this is the case where you say, look, something went wrong deeply in the security guarantees of the system. And so you have to essentially do something. Page fault, that's pretty common. Like again, go through the page table and maybe the present bit is not set, or maybe you're trying to access a page. Actually, again, I don't remember whether the general protection fault or page fault would be called if you're trying to access a kernel page from user level, right? Some floating point error. This one is actually reserved, so for Intel. Again, alignment check. Remember earlier in the class, we saw that we do the stack alignment. We said, okay, instead of just reserving 16 bytes on the stack or 3 bytes or 4 bytes on the stack or whatever, we always reserve in the increments of 16. So 16. So for example, some of these instructions, specifically vectorized SIMD instructions, require access to aligned arguments. And so if you break your alignment, this exception will be triggered, right? Machine check. This is a bad one. It means that the CPU inside detects, like, for example, a logical error, like, I don't know, like something, maybe you overheated your CPU. Maybe it was like a cosmic ray hitting it on a space station. It's not a joke today. There is a research to make sure that you can finish compute in space, right? Or maybe it's a bus error because like your connection is loose and machine says, okay, look, something really bad happened at this point. Stuff like that. So an SIMD exception is, again, SIMD is instead of like addition on an integer, it adds on multiple integers in an array, right? So that's the exceptions. Okay, cool. So let me stop here. We'll finish the table next time. We'll finish the configuration of the IDT, how it's done by x86, and we will finish the pass through the kernel, actual assembly code and a C code which implements the handler, because I mean, we kind of like didn't talk about it. And then we will also talk about the system calls, but they will be very similar to interrupts. Okay, thank you. So we'll see you then Tuesday.